This is the TS diagram for our Rankine cycle. Since the project description limits the maximum pressure of the cycle to 16 megapascals, we chose to use ammonia as our working fluid. Choosing ammonia as our working fluid, the top isobar is above the vapor dome and supercritical. This provides advantages since thermal efficiency is correlated with a higher temperature and pressure. Starting from state 1, the fluid has a superheated pressure and temperature. Then it goes through the first turbine, dropping in temperature and pressure to state 2. It reaches the reheat, which occurs at 3.4 bar and increases the temperature. Then the working fluid is sent through the second turbine at state 3. There it drops an additional amount in temperature and pressure to state 4. To complete the cycle, the fluid goes through a condenser, making it a saturated liquid at state 5. Then it gets sent through a pump to increase the temperature at state 6. This completes the cycle entirely. However, since all turbines and pumps are non-isentropic, there are states labeled 2s, 4s, and 6s. The states followed by an S are showing what the ideal cycle would look like, while the normal states show what the cycle looks like in its non-isentropic processes. According to the Maryland Power Plant and the Environment Report, a large portion of Maryland's generating capacity comes from fossil fuels. This is slightly different from what we used, since we used ammonia as our working fluid.
An issue we came across when designing our Rankine cycle was deciding on the 3 pressures we wanted our isobars to be. We decided on our first pressure to be 40 bar because that would make the power plant supercritical. We also made our lower pressure 0.07 bar because that was close to the minimum pressure that we were allowed of 0.06 bar. The problem then became what we should choose for our middle isobar, because when we decided to guess and check a bunch of values, it seemed to affect our efficiency very much, so we wanted to nail it down as best as we could. Therefore, we decided to make a parametric study comparing the different values of P2, which would be our middle isobar, against efficiency. So after doing some guessing and checking, we determined that the optimal value for P2 would be somewhere between 0.1 and 10 bar. After doing the parametric study, we determined that the best pressure would be about 3.4 bar. As you can see in our table and on our graph, this would produce a thermal efficiency of 42.16%. Therefore, we decided on 3.4 bar to be our middle isobar. Moving on to cost benefit, we had an overall budget of $18 million, and we had to buy 1 boiler, which was $5 million. We bought 2 turbines, which were each $4.5 million, and then our carbon tax due to our Q-in value was $3 million. So when we add these all together, we get a total capital cost of $18 million, which maxes out our budget. So now that we have our cost of 18, we wanted to determine what our operating cost savings would be because of our efficiency being above 39%. So after determining because our efficiency was 42.16%, we ended up making $31.6 million over its lifetime because it is above 39%. This would make the overall cost benefit $13.6 million because that is the difference between the operating cost savings and the total capital cost. Something we could have done to make our total capital cost smaller would have been to buy the refurbished turbines instead of the new ones. But we decided on buying the new turbines because they had a higher isentropic efficiency of 87% as opposed to 80%. So even though the new turbines only had a 7% better isentropic efficiency, using the new turbines yielded a better overall thermal efficiency of about 1 to 2%. And 1 to 2% efficiency better would account for between $10 to $20 million. So it was in our best interest to use the better turbines as opposed to the refurbished ones. Thus, we ended up with a total cost benefit of $13.5 million.